All right, ready for the next presentation. Um, so I'm Laure, and my colleague Magdi will also talk to you later on. We are from IMEC and University of Antwerp, so we are researchers. So what we will give you now is an idea of what will be possible in the future. So a bit different from the previous session or presentation, which clearly showed what we already can do now. A look into the future from us now. Because we will show you some experiments that we did for the Sitcom.ai project. And Sitcom.ai is one of the test and experiment facilities that is being established by the European Commission. We abbreviate these test and experiment facilities into TEFs for short. And there are many TEFs being built right now at this moment. There's a TEF for health, for manufacturing, for agri-food, but there's also one for cities and communities, so more for the smart city domain, and that's Sitcom.ai. So what does this TEF do actually? It provides facilities and infrastructure to test new AI and robotic solutions in the context of smart cities. So you can think of it as a testbed, but on a very, very large scale, because all the countries on the left are involved in Sitcom.ai. So we all work together to build this test and experiment facility. Some countries focus more on the topic of power and climate change. Others focus more on tourism and urban development. But in Belgium, we specifically focus on the topic of urban mobility and logistics. So as a company or an entity that wants to experiment with AI, you can come to this TEF, to the Belgium TEF, and we will help you with experiment design, technical and domain expertise, experimenting infrastructure and facilities, administration, legal support, ecosystem engagement. And the reason we can help you with all of that is because we have these 6 partners in the project. There's IMEC and FARI for technical expertise. We have Digital Vlaanderen and Paradigm for support in IT and digitalization. And we also have 2 cities involved in this project, the city of Mechelen in Flanders and the city of Brussels. So the mobility department of the city of Brussels is also involved in this project. So 2 very, very different cities that are involved here that we can collaborate with. And you can see on this slide one of the reasons why they are very different. On the left, you see the city of Mechelen, where I zoomed in quite a lot, because in reality, it's much smaller than Brussels, of course. And on the right, you see the city of Brussels. Well, the reason why I had to zoom in quite a lot in Mechelen was to show you where the city of Mechelen has traffic sensors. If you look really, really well into the city center, you can see 3 dots. There are 3 traffic sensors, so IoT sensors that count traffic in the city of Mechelen. When you look to the city of Brussels, it's a totally different picture. They have more than 300 of those sensors. And this is what happens very often in reality. Small and medium-sized cities do not have the same resources as the larger cities, which means often that they also don't have always the amount of data that larger cities have. That makes sense. But when you want to experiment with AI, it's far easier to do that in the city on the right than in the city on the left. Which is why we thought, can we maybe solve this issue? Can we help these smaller cities also to experiment with AI? And that's why we came up with the concept of transfer learning. Because this is how it usually works, how it traditionally works. So you train a deep learning model by giving it a lot of historical data, traffic data, if you want to predict traffic in this case, also maybe some context data, so that the model can learn the patterns, and once it knows the patterns, it can predict the future state of the traffic if you give it the current state. But this is how it can work with transfer learning. Here you do the exact same thing in one city, preferably a city that has a lot of data. So you train a model there, you make sure that it works perfectly, but then you transfer the model to a different city to make predictions in this second city. You still need to fine-tune the model with data from this second city, but our hypothesis was that you might need a lot less data than when you only train for that city. So basically combining the power of different cities to help the smaller ones. So we already had data from Mechelen and Brussels to test this idea, but we also got some data from other cities that were interested. The city of Bruges also participated, city of Hamburg as well, and we also found a large open source data set of San Diego in the United States. So we had data of 5 different cities, and we categorized them into 4 sizes of data sets. So we had the small size, in Mechelen with 3 sensors, the medium size, in Bruges with 10, large was Hamburg and Brussels because there were over 200 sensors there, and then extra large is San Diego with more than 700 data points. So with all these different data set sizes and cities, we did 3 types of transfer learning. So the first was from medium to small. That means that we first trained a model on the data of Bruges. We then transferred that model to the city of Mechelen. We fine-tuned with some data of Mechelen, and we let the model predict in Mechelen. So transferring from Bruges to Mechelen was from medium to small. We also did extra large to small, so that would be San Diego to Mechelen. And we also did extra large to large, so that's San Diego to Brussels and San Diego to Hamburg. We did these tests for 2 types of predictions. The first is predictions in time. That means that given the current state of the traffic, so the current traffic flows, that we ask the model to predict the traffic in the next timestamp. So we gave it the image with the green dots, with all the traffic counts on the green dots, and we asked the model to predict the traffic counts on these exact same dots, but a day from now, or an hour from now, or a few hours from now. The second type of prediction that we did was predictions on new locations. So this is a bit different. Here we asked the model to predict the traffic count on locations where we supposedly don't have a sensor. So we gave the model all the green data points, and we asked to predict the traffic count on the red data points. We will go through all the results in detail of these 2 types of predictions, but before we dive into the technical details, which Magdi will do, we always also made a summary blue slide before we do that. So if you're not super technical, this is the main thing that you have to remember from these experiments, this blue slide. So this is for the predictions in time, and later on we do it for predictions on location. So for predictions in time, what did we do, or what do we always have to do, is compare our method with a baseline model. The baseline model is the best model, preferably, that we can find for this specific task. Because that is the model that we would like to beat in accuracy, or that we at least have to match. So that's how it usually goes. That's also what we did. We compared with this baseline model, and we developed ourselves 2 new models. One that is very well fit to handle small data sets, and one that is fit to handle large data sets. We needed these 2 different models because we have such a big difference in data set size between the different cities. So, what do our results show? With transfer learning, we were able to improve the accuracy of the baseline model with up to 24% in the case from extra large to small. So that means that when we trained our model first in San Diego, and we then moved it to Mechelen, fine-tuned it with data from Mechelen, the predictions predictions were 24% more accurate than with the baseline model. And not only that, but we also saw that we need a significantly less amount of data in Mechelen to do so. Because we saw that if we only use 20% of the Mechelen data to fine-tune, we can already match the accuracy of the baseline model. So that was actually what we hoped for. And now Magdi will explain how exactly we got there.
Thank you, Laura. So we start with our baseline model. We have used MTGNN as our baseline. It's an open source model that everyone can get and use. So this model, or every model, takes the time series data, the data you can get from loop detectors, you can get from trajectories from FCD or cameras. And then it can also take external features such as weather information or some static features like type of the road, number of lanes. And it also takes an adjacency matrix to help capture the spatial dependencies. The model has three main components. It has a graph learning layer. It learns the a structural dependency from time series itself. So if you don't have any adjacency matrix, it works. You have graph convolution layers that learns how different locations in the city interact with each other, and we have temporal convolutional layer that learns to model the traffic data in time. So the temporal dependency, how the model is going to, how the traffic is going to be built based in the future based on what was happened in the past. And at the end, by combining it, we are going to get our predictions. So this MTGNN is one of the state-of-the-art models. It's a small model, and you can train it very easily. As I mentioned, it has, supports external features, but it's not transfer friendly, so it has node-specific components. So when you train it on a city and you want to apply it on another city, you have to remove some components and reinitiate them. Then we propose our first model. We call it a small model, and it's an encoder-decoder architecture. We have designed this to be transfer friendly, so it doesn't have any components that are designed to be fit on a specific city. And then we have our large models. It has more components and parameters compared to the other ones, and it also uses some of the latest advancement in AI, like transformers and graph attention networks. But compared to the small model and our benchmark, this model is data hungry. You cannot train it from scratch on small cities. It's not going to converge. And it's also computationally expensive. It has a quadratic order for the prediction horizon and the number of sensors. But you can fine-tune it from large to small data sets. So we start with Brussels and Hamburg data. So we have around a year of data for both of these cities. We have around 350 segments in Brussels and 200 in Hamburg. And as you see, by transfer learning from San Diego, we are improving the accuracy, mean absolute error, by around 10%. And here you also see the accuracy based on the prediction horizon. So when the prediction horizon is lower, it means that we are doing like 5-minute, 15 minutes predictions. The difference in accuracy is not much, but when it's increases further, you're going to see the gap between the transfer learning model and the normal model. Here you can see a sample of the predictions. So here in the blue is the ground truth, the real data. On the red one you can see our benchmark, and the green one is our transfer learning model. So you can see especially in there are some gaps where the benchmark overshoots the predictions, but our model is doing better in most of the cases. Here you can see the results for Hamburg and the time series for Hamburg, and here we are also doing a bit better than the benchmark. Then we have our experiments for Mechelen. In Mechelen, on the first row, you see our baseline without transfer learning. We have an MA of 25.51. As I mentioned, the MTGNN benchmark is not really a good model for transfer learning. So with transfer learning, our accuracy gets worse. And then we have our first proposed model, the small model. Without transfer learning, it does a bit worse than our benchmark, but with transfer learning, you can see the MAE lowers from 25.5 to 24 and 23.78 without and with using weather and geospatial data. But finally, when we are using a large model, the model that was trained from San Diego, you can see the MAE, we have a reduction of from 25 to 19.5, and it's a huge improvement. Here we can see some of our predictions. So these predictions happened 4 hours before the traffic happened. So we can see that most of the time we can make predictions on the uptick in the people flow in Mechelen, and also when it's going down. And here we see that for our 8-hour predictions. And then on the next test, we have done some experiments on using a limited amount of data that we have for Mechelen. So here we see that it starts from 10% and goes up to 100%. And our observation is here is that by doing transfer learning, we didn't get any meaningful improvement from using 80% of the data compared to 100% of the data. But you can also see that when we have 20%, between 20 and 30% of the data, we are getting with this model we are getting an accuracy comparable to our benchmark. So instead of let's say having to wait a few months to gather enough historical data, you can start in weeks by using transfer learning. And here we are doing this for another prediction horizon. The last one was for 4-hour prediction horizon. This one is for 8-hour, and we come to the same conclusion here as well. So that was the prediction in time. Then we are moving on to the predictions on locations. So here in this task, we are proposing a method to combine deep learnings on graph with physical traffic simulation. And we are going to show you that this approach is improving the accuracy by 10%, but our transfer learning experiments results are not conclusive. So what we are going to do here is that here you see 2 cities, and some segments are colored green and some others are colored in red. So each of these dots, they can be a loop detector, they can be a camera, or any other measuring devices. And these red ones are masked, so the model hasn't seen them during the training. So the idea is that if we can make a model to use the data from the green nodes to make a predictions on the traffic measurements on the red nodes, we can save costs on installing loop detectors in cities. So it can be it can help us get a global coverage, and without having to install a sensor in every street. So it might get too technical here, but yeah, we are masking 20% of the nodes, and we call them hold nodes, and these nodes are not visible to the model, and for the rest of the 80%, we are randomly selecting and masking them to teach the model to make predictions on them. So this is the architecture of the model. It's currently it's preprint, but it's under review in a journal. And here we have this adjacency matrix. It's calculated based on the driving distance between the locations. We have our time series. It can be traffic speed, traffic flow. We have static features. These are features you can get from, or let's say, OpenStreetMap or physical traffic simulations. Also, we have these cyclical time features that are just let the model know what time of day it is or what day of week it is. And then, yeah, these are combined with each other, and we use diffusion graph convolutions with feature-wise linear modulations and transformers to make these estimations accurately. I'm gonna skip those. So here we can see some of the results on our model versus our benchmark. The real traffic count is shown in blue. On the green line, you can see our model's predictions, and the red one is our benchmark. And you see that the red one cannot capture the scale of the traffic on these locations accurately, because it doesn't have any idea how the traffic is performing there. But here we are, with the help of the simulation results, the physical simulation models, our model can do a better job. It's not perfect yet, but it's a huge improvement compared to the benchmark. Here we also see another experiment where the benchmark completely fails, but we are doing a good job of making these predictions. Another chart, and another chart in Hamburg. So here we have our results. As you can see that with transfer learning we couldn't get any improvement. Actually, in Brussels it was worse, but we see a really insignificant improvement in Hamburg, so it's not something to count on. So that was our presentation, and thank you. Any questions or?
Okay. Are you able to complete your model with something who can interfere with the traffic, like a suggestion of another driveway, like the Bison Futé in France, for example, to have an impact on traffic, or having an estimation of the work on the roads? This can, in fact, increase the efficiency of your model, because the impact of work on road of course, we strengthen some points and highlight some.
Thank you for the question. Actually, we are writing a proposal that we want to include event data, and event data, it can be like a concert, or it can also be a road work, and we want to include them in our model to make predictions more accurate. And for the optimization task, that suggesting the users take another route, it's another task. It's not what we are doing here, but yeah, they can also consider these roadworks and such.
And did you use Google Maps to enforce your prediction or not?
We did use geospatial features, but not of Google Maps.
Yeah, we used from data from OpenStreetMap and some from national databases. Do you have the
Yeah,
names?
only public data.
Yeah, it was mainly data about like the shape of the street, how many lanes it has, because that helps to estimate the traffic flow on that specific spot. And you also used weather data because that also has an influence on mainly how many pedestrians and cyclists there are. And adding those features also improved the accuracy of the
Yes.
model. So that makes sense too.
It was 1% improvement in accuracy. Thank you.
No other questions? One more? Yeah.
The question on slide 25,
20.
because
Okay.
This one?
25. Yes, this one. At 6 o'clock, you can see that the baseline is a bit up comparing to the
Overshooting, yeah.
real. So I was wondering if the default are also transmitted from the baseline to the new model, and how you can avoid that kind of transmission of default.
What do you mean by default?
Because if at some point the baseline model has a, I don't know, overestimation of traffic of that kind of way off in time or something like that, are those errors also transferred to the model you built?
Okay, so yeah, the model we built is a different architecture, so the errors in the baseline is not going to directly affect the traffic predictions of our models. But I can also see why the baselines made this error. So it's 6 a.m. So there isn't really much traffic before, and so what you expect in 6 a.m. is free flow traffic, where its congestion is going to build up in, let's say, 30 minutes. So it can be some kind of guessing what is going to happen, because before that you don't have many traffic, so the traffic is the causality is not significant between the traffic on 6 a.m. to 5 a.m. because you don't have a congestion at 5 a.m. But you can say that at 5 p.m. to 6 p.m. the traffic of 5 p.m. is going to affect the traffic of 6 p.m. Much more significantly. So it can be that this model has seen many times that in 6 a.m. The traffic was on this location, we expect 50 cars, and it couldn't fix improve those accuracy based on like what day of the week it is, or is it a holiday or not. So all these things that can externally affect how the traffic behaves.
Okay. And so there you have some kind of knowledge of how the traffic works. Is that also in your model? Is that physics informed?
So it's not a physics informed model, but we are for our transfer learning model, we are training it we pre-trained the model with 5 years of data and around 800 sensors. So the model parameters are learning how the traffic behaves. So and
Okay.
it's also a spatiotemporal model. So it can learn how the different locations interact with each other. So if you see a congestion here, and it may know that this congestion is going to propagate to the other location in 30 minutes, so that's going to be considered in the model. But it's not a physics informed model. I've done experiments with physics informed models, but the thing is that these sensors are located from each other. Like let's say they have 500 meters apart, and in physics informed model we want to have make a continuous assumptions between the locations, and it's not easily doable in this scenario. So what you see in the predictions on locations, instead of doing the physics informed model, I run a traffic simulation, a basic traffic simulation on Sumo, and instead of having those physics inside the model, I just use the output of the output of Sumo to the model. So it makes it a lot easier to implement, and it also improves the accuracy.
Okay.
Thank you.
Okay.
Thank you.
Thanks.